All right, let's get right into it. Ethereum has this absolutely massive vision, right? To be a single global computer that nobody owns, a decentralized world computer. But, a vision that big comes with a huge challenge. How do you constantly upgrade and evolve something so massive and so decentralized? It's basically a fight for its own future, and it's all happening right out in the open.
And that really gets to the heart of the question we're digging into here. When there's no CEO, no single person calling the shots, how on earth do you make decisions? How do you fix things and move forward? I mean, this isn't just some technical puzzle, it's a social and economic one, and it all boils down to one core principle.
And that principle, of course, is decentralization. It's this core idea of spreading power out so that no single person or company can control the whole thing. So every single proposed upgrade, every new bit of code, it has to be measured against this one ideal. Does it make the network stronger and more distributed, or does it accidentally create new centers of power? It's this constant tightrope walk that Ethereum is on.
Which brings us to our first major battle, the fight for fairness. Because it turns out, the very act of processing transactions on Ethereum was creating this kind of hidden economy, almost like a hidden tax, that was making the system a lot less fair for the average user.
So this hidden tax, it actually has a name, maximal extractable value, or MEV for short. To put it simply, it's the extra profit that the people building the blocks of transactions, the validators, can skim off the top by cleverly rearranging those transactions. They could see a big trade about to happen, jump in line ahead of it, and pocket the difference. And this created this huge, unfair advantage for the most powerful players, threatening to centralize the entire network around them.
So the community came up with this really clever solution called Proposer-Builder Separation, or PBS. Basically, it splits the job in two. In the old system, one validator did everything. But in the new system, you have these specialized builders who just focus on one thing, arranging transactions to build the most profitable block possible. Then, a separate proposer just has to pick the winning block and add it to the chain. The whole idea was to break up that concentration of power.
And did it work? Well, from a money standpoint, the incentive was absolutely massive. Proposers, we're talking the everyday validators who secure the network, they saw their revenue jump by a staggering 261%. I mean, with that kind of economic boost, you can bet the new system got adopted fast. But, and there's always a but, this solution created a brand new problem.
And what's so fascinating here is the new tension this whole thing creates. You look at the chart, and while the proposers are making great money, the super specialized builders, the ones doing all the really heavy, complex work, they're left with just 3.5% of the total rewards. And that raises a really critical question. If building blocks isn't all that profitable, are the best builders just going to leave? And could that, create new security risks for the network down the line? The battle for fairness, it's definitely not over.
All right, on to the next front, the battle for scale. For Ethereum to really be this world computer, it's got to be fast and cheap enough for everyone to use. But making it faster often comes with a trade-off that, you guessed it, threatens decentralization all over again.
A huge part of the scaling strategy is using something called Layer 2 rollups. The easiest way to think about them is like express toll roads built right alongside the main Ethereum highway. They bundle up thousands of transactions, process them super cheaply off to the side, and then just post a tiny summary back to the main chain. It's a brilliant way to handle all that traffic.
Okay, but that leads to a new puzzle, right? If these rollups are posting huge amounts of summarized data back, how can we be sure that data is actually, available for anyone to check? Because if nobody can verify it, we're just blindly trusting them. And if you force every validator to download all of it, then we're right back to square one with a slow, clogged network.
The solution here is this really cool innovation called Data Availability Sampling, or DAS. And honestly, it's basically a cryptographic magic trick. Instead of having to download the entire chunk of data from a rollup, a validator just needs to download a few tiny random pieces. And just by successfully grabbing those random samples, they can be mathematically certain that the whole block of data is available without ever having to download all of it. Super clever.
But even with these clever tricks, there's always a cost. More data, more complex stuff happening, it just means validators need more powerful computers. And this quote from a developer discussion really gets to the economic reality of it. The bottom line is, if the hardware costs get too high, you start to push out the small, at-home validators, the very people that keep the network decentralized in the first place. The goal is to keep that hardware budget manageable. Something like 10% of what a validator earns in a year.
So that brings us to our third and final battle, the fight for privacy. Now, Ethereum is a public ledger. That means every single transaction is visible to everyone. And while that transparency is great for things like auditing, it's a huge problem if you want to build apps that handle sensitive, private information. It's a real paradox.
The breakthrough tech here is something called zero-knowledge proofs, or ZKPs. You can think of them as a form of digital magic. They let you prove that a statement is true without revealing any of the secret info behind it. So you could prove you're over 18 without showing your birthday, or prove you have enough money for a purchase without revealing your entire bank balance. It's a mind-blowing potential solution to that privacy paradox.
And what ZKPs are doing is enabling a whole new way of building things. We're moving away from the old model, with languages like Solidity, where everything is just public by default. And we're moving towards these new ZK-native languages, like Noir and Leo, that let developers build apps that are private from the ground up, private by design. It's a fundamental shift.
I mean, the potential here is just massive. We're talking about truly confidential financial transactions, secure and anonymous voting systems, all running on a completely public and verifiable blockchain. But as with every other solution we've looked at, this incredible power comes with a new and very steep trade-off.
And that trade-off is all about the hardware. Creating these incredibly complex zero-knowledge proofs is just computationally intense. To give you an idea, an early version of a machine that generates these proofs for ZK Sync required a GPU with a minimum of 40 gigabytes of VRAM. That is an enormous amount of power, way more than what most people have at home.
Now, the good news is the teams building this tech are totally aware of this problem. This quote here from a ZK Sync team member on Reddit says it all, right? They know that if only a few big players can afford the supercomputers needed to generate these proofs, the whole system just becomes centralized again. So the race is on to make this magic accessible to everybody.
So let's just take a step back. We've walked through three huge battles, the fights for fairness, for scale, and for privacy. And I think a pretty clear pattern has emerged. Every time there's a solution, it seems to create a new, complicated problem. It almost feels like an unwinnable war.
This table really just lays it all out, nice and clear. I mean, look at the pattern here. For fairness, we fight MEV centralization with PBS, but then we get this new trade-off with builder security. For scale, L2s solve high fees, but then validator hardware costs start creeping up. For privacy, ZKPs are revolutionary, but they come with these insane hardware demands. You see, every single solution introduces a new, complex problem. It's a constant, delicate balancing act.
And this, really, is the core takeaway. There are no easy fixes here. Upgrading a decentralized network isn't about finding some single right answer. It's about navigating these fundamental tensions between being efficient and being decentralized, between being transparent and being private, and doing it all in real time with billions of dollars on the line. It's messy.
Which leaves us with one final, kind of provocative question. What if this constant struggle, this chaotic, unending search for balance, what if it isn't a bug? What if it's the most important feature? Maybe, just maybe, it's this constant, open debate and these incredibly difficult trade-offs that make a decentralized system like Ethereum so resilient, so anti-fragile, and, in the end, so revolutionary.